everybody. Welcome back to Monte Carlo methods. When we last left off, we were talking about the empirical distribution function, which is an estimated version of the CDF from data, or in our case, simulated values. We have a target distribution with some CDF, and then we have what we got in our simulation, and we're going to use those values to estimate the CDF that we're simulating from, and I hope it's the target distribution. So we want that empirical CDF to get close to the target CDF. There's already theory in place that says the empirical CDF is definitely going to get close to the CDF that the data is generated from. But if our target is not what we're generating from, then we have problems. So we've got an empirical CDF, a true CDF for that underlying process or simulation, and then what we're actually trying to get. And if our simulation is wrong, then we may be talking about three different things. But if our simulation is right, then we're talking about two things, an empirical CDF and a target CDF, if that makes sense. So suppose that capital X1 through capital Xn are a random sample for a continuous univariate distribution from a distribution with a CDF capital F. At the end of the last video, I introduced the Kolmogorov-Smirnov statistic. It's a distance of sorts. I called it d sub n, and this is going to be the maximum distance over all x values between the empirical CDF step function and the target CDF. Again, it is known that the empirical CDF is approaching the true CDF for the simulated values, but the question is it approaching the target, the thing we're trying to simulate from? Because if we're doing something wrong, we're still simulating values from some distribution, just not the target we're going for. So we're going to look at the statistic, and we're going to reject the idea that the sample or simulated values are coming from the target distribution with CDF F if Dn is large. So I've got an empirical CDF from data, and I've got capital F, which is my target, and this should be getting small, hopefully. And if it's not, then we're going to say something is wrong. I reject that the simulation is working correctly. There's a really famous theorem in probability known as the Glavenko-Cantelli theorem, which does say that the empirical CDF is approaching the true CDF that you were simulating from. And the question again is it actually approaching the CDF that we're trying to simulate from? So if this is the CDF we're trying to simulate from, and this is what we're seeing from our simulated results, we want Dn to be small. And if it gets too large, we're going to worry that something is wrong with our simulation. At this point, we don't know how to simulate anything except uniforms using a built-in random number generator. And that's what we're working towards in today's video, testing a uniform random number generator using this Kolmogorov-Smirnov statistic. As a quick aside, suppose that X is a continuous random variable with some CDF capital F. I'm going to define a new random variable. I'm going to call it capital Y by plugging capital X into its own CDF. A CDF alone is not anything random, it's just a function. But if I put a random input in, then I'll get something unknown and random out. And I'm going to call that Y. And I claim that Y has a uniform 0-1 distribution. So let's prove this. It's going to be pretty quick, especially if I assume that F is invertible. This is not a requirement here, but this is just an aside for today, so I don't want to go too off track. We will, in fact, end up proving this for non-invertible functions later in the course. So let's assume that capital F is invertible. If it's invertible, then it's strictly increasing because any CDF is non-decreasing. It's accumulating probability, and then maybe for a while it's not accumulating anything, but it will start accumulating again. So it's never going down, but it could flatten out. But if I assume it's invertible, it's not flattening out and therefore is strictly increasing. And this means that F inverse is also strictly increasing. If you doubt that, you could show it with algebra. I understand thinking, well, it's increasing, so the inverse is decreasing. I understand the thought process, but it's really easy to see just if you sketch a picture. You know, if you sketch an increasing function, the inverse is a mirror image over the line y equals x. And when you flip that, it's still going to be increasing, even if it has changed concavity, for example. The first thing I'd like you to note here is that our y random variable is defined by plugging things into this function, capital F, which is a probability. And so the y is only going to take values between 0 and 1. So that's part way towards showing that y has a uniform 0-1 distribution. It's at least in the right space. Let's write down the CDF for y. I'm going to call this capital F sub y of y. By definition, this is the probability that capital Y is less than or equal to little y. All I know about capital Y is that it's capital F of capital X. So I'm going to plug that in. And because I know that X behaves according to this CDF, I want to isolate that X. So I'm going to take F inverse on both sides here. Because it's increasing, I am not going to flip the inequality or mess up the inequality in any way. And we end up with the probability that capital X is less than or equal to F inverse of little y. The probability that capital X is less than or equal to anything, this is the CDF for X evaluated at that thing. So this is going to be, in particular, the capital F, the CDF for X, evaluated at this capital F inverse of Y. We get cancellation and we get Y. Some of you might recognize this as the CDF for the uniform 0, 1, but more of us are comfortable with probability density functions. So if that's you, take the derivative to get to the PDF. And it's easy to see that the PDF for Y is 1. And when you combine this with the fact that Y takes on values between 0 and 1, we have now shown that Y has a uniform 0, 1 distribution. So that aside is over. Now I have a claim that is actually more central to what we're doing today. We want to look at how that Kolmogorov-Smirnov statistic, capital DN, behaves so that we know what is aberrant behavior, what is too far from 0. And I have a really fun claim for you, and that is that the distribution of the Kolmogorov-Smirnov statistic does not depend on the underlying CDF, capital F, the CDF or distribution for the X's on which we build the statistic, which seems a little nuts. The DN statistic looks like this. And it looks like it's dependent on the CDF capital F for the underlying distribution. I see it right here, but I claim that the distribution, it acts the way it acts, is actually independent of this F. Let's prove it. Again, I'm going to prove it for invertible F just for brevity. So suppose that capital F is invertible, a CDF is non-decreasing. So if it's invertible, it's actually strictly increasing. So F inverse exists because I just said it existed, but with a strictly increasing function, it would exist from that fact as well. F inverse exists and is also strictly increasing. Now let's look at the statistic, the Kolmogorov-Smirnov statistic. It looks like this, and we have to maximize this by running over all the x's on the x-axis, in theory from minus infinity to infinity. Note that because my F is strictly increasing, it is a nice one-to-one function. And so for every x you plug in, there's a single y corresponding to that x. In other words, each x can be written as F inverse of y for some y between 0 and 1, which is what comes out of any CDF. The range of values is from 0 to 1. So I think if we transform to looking at the y-axis, we have a lot less values to consider. Let's do it. What I'm trying to say is the Kolmogorov-Smirnov statistic can be written as the maximum over all y's between 0 and 1 of, and then we're just going to write this down, and I'm going to replace each x with F inverse of y. Let's simplify this a little bit. We're trying to get a handle on how DN behaves. Certainly over here, I've got an F and an F inverse, and I get cancellation there. So I do want to hone in on this term right here. In the last video, we wrote down a nice expression for the empirical CDF in terms of an average, a sample mean of some indicators. I'll remind you of that right here. And now I'm going to plug capital F inverse of y right in here for this x, which means I'm going to plug it right over here. So let's look at this term. The empirical CDF with F inverse y plugged in is actually 1 over n. The sum as I goes from 1 to n of the indicator that says that xi, capital Xi, is less than or equal to capital F inverse of y. I'm going to apply capital F to both sides of this inequality to get an equivalent sort of event. We did say that capital F was strictly increasing here. And we end up with this indicator and the indicated event being capital F of capital Xi is less than or equal to y. But what did we just say about something like this? When you plug a random variable into its own CDF, you get something that has a uniform 0, 1 distribution. I could make this whole analysis easier if I just replace this term right here with something like a capital U sub I, where U sub I has a uniform 0, 1 distribution. I'll remind you one more time that we are trying to look at the behavior of D sub n. So I'm looking at, if I do this, something that has the same distribution and acts the same as the Kolmogorov-Smirnov statistic. When it actually comes down to performing the test, you better use your data and your CDF. I'm just saying we could transform to different things as long as it will still act the same in our quest to figure out how it should be acting. How large, how far away from 0 is a number that's too big for the Kolmogorov-Smirnov statistic, which is supposed to be getting very small. So now we know that the dn has the same distribution as the maximum over all y between 0 and 1 of 1 over n times the sum as I goes from 1 to n of the indicator that says capital U sub I is less than or equal to y, all of this minus y, for capital U1 through capital UN, IID uniform 0, 1. We had uniform 0, 1 anytime we plugged a capital X into its own CDF. The independent part here is inherited from the independence of the different X values, so they're each put through the function alone, and no dependence is being created there, so I claim they're still independent. But look at this. This expression does not depend on F. The distribution of this expression, if you wanted to get into it, you would be looking at the distribution of uniform 0, 1 random variables and not be considering the original CDF at all. And this is what we wanted to show in this claim, that the distribution of the Kolmogorov-Smirnov statistic does not depend on the underlying distribution with CDF capital F. Yet again, I ask, what is the distribution of dn, and how large should dn be for us to think that our simulation is going wrong? Without loss of generality, we just saw that we can assume that the underlying data, I'm going to call them capital X1 through capital Xn, are actually IID uniform 0, 1. If you want to preserve the capital X1 through capital Xn that we started with, you could call these U1 through UN, but I'm just kind of reusing the name. So for a uniform 0, 1 distribution, the CDF, capital F of X, is just X for X between 0 and 1. It's also defined to be 0 when X is less than 0, and 1 for any X plugged in that's greater than 1. This is the CDF for the uniform distribution, and I want to use this when trying to compute or look at the distribution of the Kolmogorov-Smirnov statistic. Note that for this CDF, the inverse of the F inverse of X is just X as well, and there was an F inverse in one of our expressions. We've written a few now. Our Kolmogorov-Smirnov statistic, dn, is currently the maximum over all y between 0 and 1 of the empirical CDF evaluated at F inverse of y minus y, and F inverse of y, if we assume that capital F is the CDF for a uniform distribution, is just y, so I can drop down to this. How are we going to maximize this function of y over all the y's between 0 and 1? I'm going to graph this, and I'm going to make a y-axis down here, a horizontal y-axis. If you like, if this bothers you, note that the little y up here is just a dummy variable, and you can replace all the little y's here with little x's and do the same thing I'm about to do. I'm going to draw the line y equals x or x equals y, depending on how you graph this, and I'm going to imagine, say, a sample of size 4, where I get some values, say, here, 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 and here. I'm going to draw my empirical distribution function that's associated with these values. It's going to be a step function consisting of 4 steps, each with a height of 1/4. And I claim that it's easy to see. I hate to use the word easy, so I'm putting this in quotes. It is going to be something you see, whether you see it right away or have to think about it a little bit. You'll eventually convince yourself, I'm sure, that the maximum distance between this white line and this blue step function is going to occur at one of these data points. So if you're convinced of that, then great, we don't have to look at all little y's between 0 and 1. We just have to consider the deviations at these points. I want to put these points in order so we can sort of consider them from left to right rather than looking at x1 and then x2 and so on. We have a notation for this in statistics. I'm going to call the smallest value in this sample of size 4. I'm going to call it x1 in parentheses. This is different than x1 without the parentheses. And then I'm going to call the next largest value x2 in parentheses, x3 in parentheses, and x4 in parentheses. Some of you know that I'm referring to order statistics. And order statistics, there's different notations. So one of them is to use like x1 in parentheses to denote the minimum of x1 through, in general, xn, whereas x2 in parentheses is going to denote the next smallest value of x1 through xn, up through xn in parentheses, which is going to be the maximum value. Another common notation is to call these values x1 colon n, x2 colon n, up through xn colon n. And these are not IID. The minimum is always smaller than the maximum, for example. Not only are they not independent, but they're going to have different distributions, because if you imagine getting a sample over and over and over again, and then computing the minimum value, and maybe computing the maximum value, and whatever else you want to do in between, and collected those and tried to imagine a distribution for those, like by making a histogram, the minimum values are going to pile up more towards 0, whereas the maximum values are going to pile up more away from 0. So definitely not identically distributed. Going back to this picture and looking at x1 in parentheses, that's right here. We are assuming that f of x or f of y is the CDF for the uniform 0, 1 distribution. So it is just x or y. And so this CDF at this smallest value is right here. This is capital F of x1 in parentheses. And I want to compare it to this height of 1/4 and this height down here of 0. In general, if n was more general, I would want to compare this value right here, this CDF, with this minimum value plugged in. I'd want to compare it to a height of 1/n at a height of 0. Similarly, on this picture, if I look at this x2 in parentheses, f of x2 in parentheses is right here. It is this point on this line, y equals x. And I want to compare it to this height of 1/2 and down here to this height of 1/4. In this picture, it's clearly further away from 1/2 than it is 1/4, but that's what we want to do in general. So let's compare the CDF at the second largest order statistic. And because the CDF, capital F of x, is x, this is just the second largest order statistic. I want to compare this to 1/2 and 1/4, but more generally to 2/n and 2 minus 1/n. And I'm going to continue in this way for all of these points. I want to compute the maximum distance. I'm going to focus first on the above distances and then the below distances. In summary, dn is a maximum of things like this. We noted that the maximum has to occur at one of these points, so we really have to check n points, or in this example, 4 points. And we've got above distances and below distances, so I'm going to break those up. I'm going to define dn plus to be the maximum as I goes from 1 to n of the ith order statistic minus I over n in absolute value. So that's a distance, right? One of those distances. And then dn minus to be the other one. So the maximum as I goes from 1 to n of the absolute value of the ith order statistic and the quantity I minus 1 over n. Then we can get dn by maximizing over these two things. We're trying to find the distribution of dn. Spoiler alert, it's not going to happen, but we will get a handle on its behavior. You may recall from mathematical statistics, it's okay if you don't know it, that the order statistics for IID uniform 0, 1 random variables have beta distributions. That is not going to be helpful here because that's not exactly what we're talking about. That would mean that each of these xi's in parentheses have beta distributions, but we're subtracting off values, taking absolute values, doing other maximums on top of that. And in the end, this dn plus and dn minus do not have nice known name distributions. In the 1930s, Kolmogorov and Smirnov showed that the limit as n goes to infinity of the probability of the square root of n times the statistic that we're working with being less than or equal to x is equal to this expression here. It doesn't look like too much fun to work with, but there's a lot of information in it that I think we can use. Our hypothesis test here, our null hypothesis is going to be that the simulated values, capital X1 through capital Xn, come from a distribution with target CDF capital F. Our alternate hypothesis is going to be not the null hypothesis. Easy enough. Our test is going to be to reject the null hypothesis in favor of the alternative if dn is greater than some cutoff value c, also known as a critical value. This is computed in hypothesis testing by saying, even if I'm doing the right thing, occasionally I'm going to get a funky sample and dn is going to be large anyway. So let's try to say, I want to get this right most of the time. I'm going to find a c for which the probability of being greater than c is some small number that I'm going to sort of preset before going into this test. It's usually denoted by an alpha. If you've had hypothesis testing, this is the level of significance of the hypothesis test. So someone sets an alpha for you. It's like a tolerance for error. And then using this and our previous approximation for how dn behaves from Kolmogorov and Smirnov, we're going to try to figure out a cutoff to use once someone has prescribed an alpha for us. What people usually do is they say, if I have a large sample, then I'm going to ignore the limit. I'm going to say that the probability the square root of n times dn is less than or equal to x is approximately equal to the value I'm supposed to get in the limit. Let's move the square root of n to the other side over here. And can we figure out how to get a quantity like this to equal a pre-specified alpha? I decided to take a look at this quantity numerically and graphically. You'll notice there's no n on the right-hand side of this expression, so what I'm about to graph does not depend on our sample size. I picked several values of x, many values, and fixed x, and then I ran this sum out for a very long time, like 500,000 terms in each sum. So for every fixed x, I ran the sum from j equals 1 to 500,000 and computed a number. And here's the graph I got when doing this for a ton of little finely partitioned x values. I get a very nice looking curve. Just for fun, I threw a couple of values of alpha up here, some of the most common values in hypothesis testing, the most common being, I think, alpha equals 0.05. If I put that here, and I want this, and if this curve represents this quantity, and I want this quantity to equal 0.05, then what I'm looking for is the x value right here, which turned out to be around 1.3581. And just as another alpha value, if I use 0.1, and I want to see when this quantity is equal to 0.1, that means I want to see where this curve passes the line at y equals 0.1. And this one turned out to be approximately 1.2239. So let's go back to the first one when alpha is 0.05. What this is saying is the probability that the Kolmogorov-Smirnov statistic is greater than 1.3581 divided by the square root of n is approximately 0.05. This is how we're going to compute a cutoff for a given n as long as n is large, because this all came from an asymptotic result of Kolmogorov and Smirnov. People have worked out and tabulated many different critical values. We just worked out two of them numerically, and they have worked out critical values in the small sample case as well. I'm going to be looking at a sample of size 100,000 that is pretty solidly in the large sample regime. And so here are some tabulated critical values that people use. A value of C in order to get this probability to be alpha. Here's two of the ones that we saw ourselves. And these are known to be good approximations for C whenever n is greater than 40. If n is less than 40 and you need to do a Kolmogorov-Smirnov test, you can find a Kolmogorov-Smirnov table, I'm sure. There's also a built-in Kolmogorov-Smirnov test in R that we'll talk about. But remember, no black boxes in here. Here is the bottom line. If you're just tuning in now, this is really all you need. Sorry, everyone else that was here from the beginning. You have simulated values, capital X1 through capital Xn, from a target distribution with CDF capital F. You compute this quantity, dn plus and dn minus, that looks like this and this. Do not use capital F of x equals x. This is only if your capital F is the CDF for a uniform 0-1 distribution. You have a target distribution with a given CDF that may or may not be uniform. I switched to the uniform when doing the theory, but now that we're actually computing what we're seeing, the theory tells us what we're supposed to see, but what you're actually seeing has to use the actual CDF you're working with. So don't use f of x equals x when computing the Kolmogorov-Smirnov statistic. It was only an intermediate step to get a handle on the distribution. You then want to compute the Kolmogorov-Smirnov statistic by maxing over your dn plus and your dn minus. Then you choose an alpha for your test, for example, 0.05. And then if n is greater than 40, you hope that your Kolmogorov-Smirnov statistic dn does not exceed the value of c given in the table. In my case, for an alpha of 0.05, this c is going to be 1.3581 over the square root of n. Otherwise, your simulation has failed the test. So before we finish up today, I want to do a quick example that is completely not realistic, but it's something you can use if you wanted to try some of these computations by hand just to make sure you understood what was going on. In the next video, we're going to do something much more realistic in R. Suppose I've used a built-in random number generator to generate a sample of size 7 from a uniform distribution and got this output. Now, this is horrible output. There's a lot of rounding here. You should never do that for your uniform draws. I am doing it not only to have a nice slide, but to also have some nice computations ahead. And this is for you to use, again, if you're just trying to do this by hand. I computed dn plus and dn minus. I actually kept all these fractions, like this is 6/10, 2/10, etc. And I got dn plus as 9/35 and dn minus as 4/35. So if you want to try it and you get those numbers, then you know exactly how to compute these two things. dn plus is approximately 2.57 something, and dn minus is approximately 0.114 something. And so dn, being the maximum of these two, is approximately the 0.257 something. I haven't told you anything about small sample critical values, but the tabulated critical value when n equals 7 and alpha equals 0.05 is actually 0.483. So this is another thing you might use this exercise to check for. Would you know how to find a tabulated critical value either on paper or in R? And so here's an example. If you want to look up the tabulated critical value, make sure you can match this number. Now, my Kolmogorov-Smirnov statistic, which came out to be 2.257 something, is smaller than 0.483. So I've passed this test for uniformity, even though I have a very, very horrible fake data set. The reason I passed is because the sample size is quite small and we really can't get a good picture of anything. The small sample test, any small sample hypothesis test, is quite forgiving as well because it knows you're not going to get a good picture of anything. So it's saying, the difference is not egregious, if that makes sense. But in the next video, I promise to do a much more realistic test in R. So I hope to see you in the next one.